The major part of this work is the physical-chemical properties investigations of fuel and fission product chemistry. We also have developed a database on fluoride and chloride salt, where we introduce all data which are produced by the different techniques. And last not least, also some irradiation work, and also followed by some PIE on the materials which have been irradiated. I think this is also a key activity or an essential activity in support to modeling work, because validation verification is always essential to develop applicable models in the various fields, also in this one. Our goal is, first of all, in using these labs, to have experimental validation of the fuel performance, to better understand the fission product chemistry, and there are some unknowns, as we have heard also during the day. We try to find a way to control the redox potential of the salt, a very important factor here, also to have this parameter under control, and also to find the best way for the cleanup. So we have some activities also in this area. The challenge that we have is first purity of the materials. So recently we have installed a so-called HF line, a very big project, because also we're dealing with the safety authorities. It's not easy to get permission to install such a facility. Finally, we managed to have such a facility in our premises, and I think this is very important regarding this molten salt work. So purity of materials, we use this HF, and also for the synthesis of the starting materials. We have also, of course, to deal with the container materials to avoid corrosion, to avoid vaporization. So our activities, or we use for our activities, mainly nickel-based or boron nitride container materials, and we have developed efficient encapsulation to avoid any vaporization or release of material during the tests. So the first step, the synthesis of the actinide fluorides. So we have this gas line, as I said, with an Inconel fluorination reactor, which is underneath, the furnace is underneath of this glove box, and the reactor is placed in this furnace from the inner of the glove box. So we use as the starting material the oxides, the thorium oxide, uranium, and plutonium oxide, with best possible purity, and then we synthesize the corresponding fluorides with this fluoride line. So we produce, for instance, in the case of uranium, UF4, plutonium, plutonium-4, but also thorium fluorides, and also with introduction of hydrogen, we can adjust the valency or the stoichiometry of the actinide fluoride. So the first check after the synthesis of the starting materials, which is very important to be sure about the purity of this material that you have produced. The first one is the color check. You see from the color how complete your reaction is as a first indicator. Weight balance is a second indicator. And then we make this determination of the thermal gravimetry with this melting point determination. And we see that, for instance, in the case of the red curve, that we have an incomplete reaction, so that we have still oxides present in this compound, and only in the blue curve we see that the fluorination, in this case of thorium fluoride, is complete. And last not least, also an XRD phase analysis, where we use three systems, the experimental work, the calculation work, and the data which are found in the database, and try to make a comparison and an identification of the different peaks, also indicating or a good indicator for the purity of the product that is obtained, in this case the plutonium fluoride. Then I said the important step we think is that we can also offer the possibility to have irradiation experiments. In this case, the so-called salient irradiation of molten salt in the HFR reactor. So in fact, this is a cooperation between us and Energy in the Netherlands. So in fact, the JRC is still the owner of the reactor, so we we have not yet given ownership to HFR. HFR is the operator and the user of this facility, so we have developed this project in common. So developed this capsule, which of course is made of corrosion-resistant material in this graphite crucible, then an open container with the metallic filter to accommodate the fission gas release, and the crucible with temperature resistant and also a neutron fluence monitored through activation. So this capsule is under irradiation in the reactor now, and we expect that we will have some very interesting and important data when we will make the PIE work, or the post-irradiation, the characterization of the material after the irradiation process. Then our major tool that we use for the phase diagram studies is these special capsules with the boron nitride or nickel containers, which needs to be completely sealed tight in order to, as I said, avoid vaporization. And all these activities are done also because we use, in addition to uranium and plutonium, also the plutonium. We need to work inside of a glove box, of course, and where we have the differential calorimeter, which is used for these phase diagram studies. So this is the system again, and you see then the data which are being used. So we have these curves which are registered for the melting point. So we have the onset of the melting process, and then also the end, the offset point, where the complete sample is liquid in the container. And then we include this data in the phase diagram, and additionally to the experimental work, we try to verify the validity of this data, or to check this with the fact-safe calculation program. Then this I might skip because it has been explained very well by Anna Smith this morning. So this is the mixing enthalpy. So this is this mixing phase of these two phases which are mixed with this nickel separator, and this curve, which has been explained this morning also very well by Anna Smith, give this result as they are shown on this view graph. So you see here in the first case for the verification, we have measured the enthalpy of mixing of lithium fluoride, potassium fluoride. This study was done at 1121 Kelvin, and compared to two data which were found in the literature, and you see that there's a good agreement between the data in the literature and our data, which we have measured recently, and also very well confirmed with the calculation by FactSage. And on the right-hand side, we have then the enthalpy of mixing of the lithium fluoride and thorium fluoride system. Again, two different temperatures in this case, the solid line, and which is the calculated enthalpy, again, fits very well for the two temperatures, which are very close with the experimental data which were measured. They are quite away from an earlier measurement which has been done on a similar system. Then we have also revisited this phase diagram of lithium fluoride and thorium fluoride. So you see here two graphs, where the left one is the comparison between the lithium vapor pressure as a monomer for the pure lithium fluoride liquid phase, and for different mixtures as a liquid solution. And on the right side is the comparison between the thorium fluoride and, again, the different compositions between lithium and thorium fluoride in liquid solution. And the vapor pressure for the thorium has been extrapolated also for temperatures which were lower than the melting point of the equation of the liquid state. And then all these data that were produced by the different techniques were assembled to give the final phase diagram that you see on this view graph. So you see the different techniques, and then the final result, the experimental data and the calculation of this result for the system lithium fluoride, thorium fluoride. For the vapor pressure, we have in our institute a system which is called Knudsen cell mass spectrometry, which can deliver very good data. And we use this mainly for solid fuel material, but in this case we have tried to adapt this method also for the molten salt. Especially interesting is, of course, the discussion about the cesium fluoride, because the claim that cesium fluoride is completely retained in the fuel needs to be proven, and we think that this technique can contribute to provide reliable data for this formation of a stable cesium fluoride and also the completeness of this reaction. So in fact, in the left-hand corner, you see the data that we obtain in the mass spectrometer for these different compounds, and also as a reference, as a function of the temperature which is being applied. We have compared our data, so the cesium fluoride, which you see in the middle, the blue line, or the violet purple line, and the data which are taken from the literature partly or have been calculated by ThEC. And we see that these data are essentially much higher than the measurement that we have made with this technique installed in our laboratories, which could be an indication that we have really a complete cesium fluoride. But we believe that this work needs to be continued to have a real final confirmation that we have a complete dissolution of cesium fluoride in this lithium fluoride thorium fluoride mixture. Then we have also tried to revisit the heat capacity determination of thorium fluoride and also different mixture of lithium and thorium fluoride. We have tried to improve and optimize this method, where we have applied a temperature program, as you can see, a steep increase in the beginning, but then essentially stepwise increase of temperature up to 1155 degrees Celsius, and then again the decrease, and registered the heat flux, which has been measured in the blue curve, and then making the ratio between the temperature increase and the signal that is registered in this heat flux curve. We can calculate the heat capacity at these different points, at different temperatures, and this is something that we have tried to refine, as I said, both for the thorium fluoride pure, as it is shown here on the view graph, but also for different mixtures, lithium fluoride and thorium fluoride. Then we think that also, it has been mentioned also, this morning, thermal conductivity is a very important parameter also for the study of nuclear fuel. And we have the so-called laser flash technique, which is installed also for the measurement on irradiated materials. So we can use this tool or this facility for both the non-irradiated fresh fuel and also irradiated fuel. But our expertise is clearly on the side of irradiated materials and solid materials, essentially. So for us, it was the difficult task to build or to construct a new crucible, then make a new design to optimize the data output. And this is, as it seems now, not a very easy task. And therefore, we are in the phase to develop this properly and to have reliable data on the thermal conductivity of these molten salt mixtures in the near future. So, to conclude the activities that I have shown in this presentation, so as I could show, we have a system to synthesize the starting actinide fluorides, different composition, also individual actinide fluorides. We have in our house electrochemical studies on the behavior of these materials. We have determined melting points and phase diagrams, both the experimental data, but also corresponding modeling work, taking into account, in these cases, also the fission-product effect. The same is true for vapor pressure. Then we have data on heat capacity, mixing enthalpy, which we introduced in this phase diagram, and the fission product release from the fuel, where we have a possibility to make also PIE. As I said, we want to see essentially after the irradiation of this salient fuel in the HFR to have good data on this information on these parameters. We have the database on molten salt, so this not yet complete set of data, but we are connected also to the international database on thermodynamics of advanced fuels. So it's an NEA OECD project, and we are connected to this and help to keep this updated and to complete the data which are required, still required. We have under development the idea to use also Raman in our institute, which is also used for essentially conventional fuels, to apply this also to the molten salt for structure studies. We have a PhD on thermal conductivity. As I said, this is not yet fully developed and still need to be completed. And also regarding viscosity and density, we plan to have PhD work to complete the data set on these parameters for the fuel characterization and the fuel material characterization. So just to fully conclude, so we think that there are still gaps on the physical-chemical data on molten salt reactor, different fuels, different types of fuels, different compositions. The models which are under development confirm that it seems that we have a good agreement between the experimental data and the modeling, because, as it was said also today, it's essential that we have an experimental validation of the model. And last not least, in support to member states, we tried at the JRC to have this good relationship with member states, to be involved in the international programs and use our techniques and methods that we have, that we consider, especially because they are also nuclearized, and this is what makes a special, unique character of these techniques for the actinide chemistry development in the molten salt systems. Thank you very much.
Thank you very much. Questions? Yes?
How quickly do you think you will fill in the white cells in your database for salt?
But this is the goal, that we try to find out also together in this group. There's a larger group with experts. I don't know exactly, Ondrej knows much better because he's participating in this group, and they try to define which are the most urgent data that would be needed. And if we can contribute, we would try, of course, to do so.
But no clear time?
It maybe it exists, but therefore I would not be the right person to ask this question. I can try to ask Ondrej, and he knows certainly much better what is the status of these discussions.
What do you expect would cause the change in the thermal conductivity of ionic radiation?
We are not sure that there will be a major change. I don't know. This depends very much on... It has shown, of course, this is different because we have our expertise based really on solid materials, and there you have structural influence which is changed, for instance, bubble formation, cracking, and everything, which has a big impact after irradiation. But could be that due to homogenization of the fuel, you have the gas which escapes from this fuel, so maybe that the composition has not such a big influence, but it needs to be verified, I think.
I would expect that any soluble metallic species would play a role in the thermal conductivity.
It of course depends very much also on the burn-up, on the quantity of fission products or other products that you have inside of the system.
I think it's really important research. This is probably the most interesting research going on in Europe, maybe in the world. In my opinion, it's really important. Is there any way we can help you accelerate that?
Yes, as I said, thank you very much for these encouraging words, and I will convey the message to the colleagues because they are essentially responsible for this work. And we have to defend ourselves against the general perception of nuclear in Europe also, because we are a European organization, and this makes it sometimes difficult for us to especially be involved in development programs for future reactor systems maybe. So we must always argue with the safety arguments that we justify our work. Of course, anything that the member states convey as a message to those groups or to those who decide about the future program, because we have an ongoing process where the next framework program, starting from 2021, so after the Horizon 2020, defines our activities. So if there are from the member states positive messages in this direction, then we have a better chance to define and to enlarge even maybe or enhance our activities in this field.
And how many member states do you need?
That is not it depends on how these discussions go. Very often, if you have one which is really pushing hard, maybe with the support of some others, this is not, I have participated in a few of these discussions. That's essentially how the story goes. You have someone who really stands up and makes a plea for this activity, and then you get the support. But it's not one single way such a situation can evolve or develop. So but some support would be useful.
Yeah.
Just continuing on that, how dangerous do you think the German government is to you?
Not really, because they go. As I said, we base our activities really on safety arguments, and we have under construction a completely new laboratory where the German authorities in Stuttgart, they are responsible for our laboratory. They are a green-red government with a green Minister for Environment who who is in charge of the license of our facility. And he's very proud of that he got the permission, or he got it through also with the local communes to get this new laboratory, which is really a very big one in the order of 3,000 square meter surface, where we install completely all these techniques in a very safe new environment. So they support us as long as we argue in this direction.
Now you have already shown us quite some tools, quite some results. What else do you need to get a molten salt reactor technologically on the map?
We don't see our role as the one who are really
I understand that.
We are supporting.
Yourself, your own opinion, what do you see is still lacking to put it on the map? Which technical data do you still need to provide us?
But this is more related to the question about what is missing. What are the missing data really also in this database? I think these groups should really decide on what are data that are still missing, and they should really, and if we can contribute to this or the group can contribute, I think if there's a good solution found on this issue, then I think we have made a good step forward. But this is, I would say, a task also for this group to define this data.
What is missing to build a molten salt reactor in Karlsruhe in German research center?
This is almost excluded. This is, I would say this is excluded because we got the permission for this laboratory. This does not mean that they allow us to build nuclear facilities. Especially, we have immediately, if we would make such a proposal, immediately we would have the Austrian government and some others jumping up and being there and say, this is not possible. This is completely excluded. And even there, the Germans would be against, I'm pretty sure. That would never happen.
All right, then let's thank the speaker again.
Thank you very much.